From the smallest atom to the largest galaxy, everything in the universe is in a constant state of motion. Understanding how things move is fundamental to our understanding of the universe. This is where physics comes in, the science that seeks to explain the workings of the natural world. One of the cornerstones of physics is the study of motion, a field known as mechanics. Within mechanics, kinematics focuses specifically on the description of motion. Forget forces, forget energy for now. Kinematics is all about the where, the how fast, and the how quickly that speed is changing. Imagine trying to predict where a baseball will land after a home run or design a car to stop safely. These tasks require an understanding of kinematics. Join us as we delve into the fascinating world of kinematics, exploring the principles that govern motion and their profound impact on our understanding of the universe. Kinematics is the branch of physics that describes the motion of objects. It doesn't concern itself with the causes of motion, but rather with the details of motion itself. Imagine watching a car race. You might be interested in how fast the cars are going, their positions on the track, and whether they are speeding up or slowing down. These are all aspects of kinematics. To fully grasp kinematics, we need to understand three fundamental concepts: displacement, velocity, and acceleration. These concepts provide the language we need to describe motion accurately. Over the next few sections, we'll explore these concepts in detail, providing you with the tools to understand the world in motion. Imagine you walk 10 meters forward, then turn around and walk 5 meters back. You've walked a total distance of 15 meters. But are you actually 15 meters from where you started? No. This is where displacement comes in. Displacement is the overall change in position of an object. It's not about the entire journey, just the start and finish. In our example, your displacement is only 5 meters forward because that's how far you are from your starting point. Another key difference is that displacement includes direction. It's not enough to say you moved 5 meters. You need to specify 5 meters in a specific direction, like east or west. This makes displacement a vector quantity, meaning it has both magnitude, the 5 meters, and direction. Understanding displacement is crucial in many areas of physics, from describing the motion of planets to designing efficient transportation systems. We often use the terms speed and velocity interchangeably in everyday language. However, in physics, these terms have distinct meanings. While speed tells us how fast an object is moving, velocity tells us both its speed and its direction. Imagine two cars driving side by side at 60 miles per hour. They have the same speed. But what if one is heading north and the other east? Their velocities are different, even though their speeds are the same. Like displacement, velocity is a vector quantity. It's not enough to say a car is traveling at 60 miles per hour. We need to specify 60 miles per hour to the north, south, east, or west. Velocity is essential for understanding how objects move over time and predicting their future positions. It plays a crucial role in fields such as aviation, where knowing an aircraft's velocity is critical for safe navigation. Section 5. Acceleration, beyond just going faster. When we think of acceleration, we often think of speeding up. However, in physics, acceleration encompasses any change in velocity. This means speeding up, slowing down, or even changing direction are all considered acceleration. Imagine driving a car and stepping on the gas pedal. You're accelerating, increasing your velocity. Now imagine stepping on the brakes. You're also accelerating, but this time in the opposite direction, decreasing your velocity. Even if you maintain a constant speed but turn the steering wheel, you are still accelerating. This is because you are changing the direction of your velocity, even if the magnitude, speed, remains the same. Like velocity, acceleration is a vector quantity, meaning it has both magnitude and direction. Understanding acceleration is crucial for analyzing motion in detail, from the movement of particles in an accelerator to the motion of galaxies in the universe. Section 6. Equations of motion. Predicting the future of movement. Now that we have a firm grasp of displacement, velocity, and acceleration, we can introduce the equations of motion. These equations provide a mathematical framework for describing motion with constant acceleration, allowing us to predict an object's future position and velocity. For objects moving with constant acceleration, there are 4 primary equations of motion. These equations link together displacement, initial velocity, final velocity, acceleration, and time. Don't be intimidated by the equations. They may seem complex at first glance, but with a little practice, they become powerful tools for solving problems related to motion. These equations form the bedrock of classical mechanics and are used extensively in fields such as engineering, robotics, and animation, enabling us to design, predict, and control motion with precision. Section 7. Freefall: Gravity's Influence on Motion. One of the most common examples of motion with constant acceleration is freefall. When an object is dropped near the Earth's surface, it experiences a constant downward acceleration due to gravity, approximately 9.8 meters per second squared. This means that for every second an object falls, its velocity increases by 9.8 meters per second. Whether it's a feather or a bowling ball, in the absence of air resistance, all objects fall at the same rate. The equations of motion we learned earlier can be applied to freefall, allowing us to calculate how long it takes an object to fall from a certain height or how fast it will be traveling when it hits the ground. Understanding freefall is essential in numerous applications, from calculating the trajectory of projectiles to understanding the motion of celestial bodies. Section 8. Projectile Motion: Understanding the Curve. Have you ever wondered why a baseball follows a curved path or why a basketball shot needs to be arched to make it through the hoop? This curved motion is known as projectile motion. Projectile motion is the motion of an object that is launched into the air and subject only to the force of gravity. Think of a baseball being hit or a cannonball being fired. The key to understanding projectile motion is to break it down into its horizontal and vertical components. The horizontal component of velocity remains constant, while the vertical component is affected by gravity. Analyzing projectile motion is crucial in sports, military applications, and even in understanding the movement of planets and satellites. Section 9. Circular Motion: Round and round we go. Not all motion is in a straight line. Think about the wheels of a car, the blades of a fan, or the Earth orbiting the Sun. These are all examples of circular motion. Circular motion is characterized by an object moving along a circular path at a constant speed. While the speed may be constant, the velocity is constantly changing because the direction of motion is constantly changing. This change in velocity means that an object in circular motion is always accelerating, even if its speed remains the same. This acceleration is always directed towards the center of the circle and is known as centripetal acceleration. Understanding circular motion is essential in fields such as engineering, astronomy, and even in our everyday lives, from designing efficient gears to understanding the movement of satellites. Section 10. Kinematics in Action: Real-World Applications. Kinematics is not just a theoretical concept confined to textbooks, it has countless practical applications in our everyday lives. From the design of cars and airplanes, to the development of robots and medical devices, kinematics plays a crucial role in shaping our world. Engineers use kinematics to design safer and more efficient vehicles. By understanding the principles of motion, they can optimize car crumple zones for impact absorption and design airplanes to withstand the stresses of flight. In the medical field, kinematics is used to analyze human movement, aiding in the diagnosis and treatment of injuries. Prosthetics and orthotics are also designed using kinematic principles to mimic natural movement patterns. From the mundane to the extraordinary, kinematics is an essential tool for understanding and navigating our world. Section 11. Conclusion: The importance of understanding motion. From the graceful arc of a basketball to the intricate movements of a robot, motion is all around us. Kinematics provides the language and the tools to understand this fundamental aspect of our universe. By grasping the concepts of displacement, velocity, acceleration, and the equations of motion, we gain a deeper appreciation for the world in motion. Whether you're a student, a scientist, or simply curious about the world around you, kinematics offers a fascinating glimpse into the principles that govern the universe. So next time you see an object in motion, take a moment to appreciate the intricate dance of physics at play. It's a dance that has captivated scientists and philosophers for centuries, and continues to shape our understanding of the universe today.